Welcome to a paper presentation on USBFuzz, a framework for fuzzing USB drivers by device emulation, a paper by Huiping, Purdue University, Matthias Payer, EPFL, and is presented by Wesley Black. So let's start off with the motivation. USB is supported on many devices, computers, phones, peripherals, and more. USB has a large attack surface due to there being so many devices that support USB. This also means that there are quite a few attacks that attack USB, such as the auto-run attacks, where a USB device plugged in will automatically run some software, a USB killer, and a couple other attacks. The existing methods of defending against USB attacks are limited and can be complex, often requiring filters based on known attacks or running a USB device in an isolated environment to make sure it can't do anything more than it's supposed to. The authors in this paper propose that a better solution to these complex defenses is to instead find the bugs and to patch them, which could be pretty difficult because testing drivers can be complicated, and it can be difficult to provide random inputs to test all possible cases, and even with some existing USB fuzzers, these USB fuzzers run on programmable hardware. So one of them, such as Face Dancer, can be pretty expensive, about $85, and at large scales is not very usable due to its cost. So I'm going to start off giving a background on what fuzzing is, because in order to understand what USBFuzzer does, it is important to understand fuzzing. Fuzzing is an automatic testing technique commonly used to test software behavior giving random inputs. It's typically looking for something unexpected to happen, such as a crash or hang-ups or some unexpected behaviors going on. And some fuzzers can be guided when it's selecting random inputs, building off of cases where previous input has, for example, where previous input has done more code coverage, though typically this requires some instrumentation in the target code. Some existing USB fuzzers mentioned in this paper are VUSBF and Face Dancer, which use hardware to input random data into the operating system. However, because they are hardware and separate from the actual operating system, they can't really be guided via code coverage, and because it requires hardware, it can be expensive. Another USB fuzzer, SysCaller, uses an implemented software controller to add random inputs and can take advantage of code coverage, but it's tightly coupled to Linux kernel and very specific Linux kernel versions and can't easily be ported to other operating systems. So what kind of security risks can be seen from the USB devices? Now, the authors classified the risks into three categories: attacks on implicit trust, electrical attacks, and attacks on software vulnerabilities. An attack on implicit trust allows an attacker to program a USB to add in additional actions such as a keylogger or installing malware through a mouse and keyboard inputs or overriding some settings in the operating system or stealing some files. But why would the operating system implicitly trust whatever device is being plugged in? Well, it's due to the assumptions made by the operating system and the USB standard that hardware is hard to modify, and that anything being plugged in can be trusted because it's hard to modify. Because of this assumption, it's also possible for a device to just send a high voltage through the USB power bus onto the host and just cause damage onto the host device. The final category are software vulnerabilities, which exists because code paths can't be completely tested very easily, which results in bugs that can allow an attacker's USB device to take control of the host in privilege mode. And the authors even noted one bug that they found with USBFuzz, which was a double free bug. From the three categories, USBFuzz is assuming that the threat comes from a Category 1 and from Category 3. It's assumed that the threat is coming from a physical USB device that looks like a regular USB device. Since it's a physical USB device plugged into the system, do you remember what the operating system does from the last slide? Right, it trusts that the USB device being plugged into the system can be trusted and is trustworthy because it's hardware, and hardware is hard to modify, and that because it looks like a regular USB device. And so then USBFuzz also assumes that there is a vulnerability in the host software that allows the attacker to take advantage of that vulnerability in some way through sending very specific bytes into the device that allows the attackers to accomplish whatever goal they have, be it denying the system service, so blue screen of death, crashing, through escalating the attacker's privilege to allow them to do what they want, or allowing them to execute their own code, or performing some other attack. So USBFuzz has some design requirements that the authors put out before they actually started creating USBFuzz. They wanted to make sure that it was low cost and that USBFuzz did not need hardware, because existing USBFuzzers that required hardware tended to be very expensive when scaled up to larger usages. The authors also wanted USBFuzz to be portable. They wanted it to be capable of working on any operating system without needing many modifications, and that it wouldn't be tied to any specific version of an operating system or any specific kernel version. Finally, they wanted the USB fuzzer to be able to run without needing to know a lot about the USB standard and the device, so that the interactions between the device and the host are a lot less complex. So how did the authors meet these requirements for USBFuzz being portable, being low cost without needing hardware, and being able to provide randomized inputs but still guided by code coverage? Well, they decided to use an emulated device to give randomized inputs into a target located on a virtual machine. This allowed it to be cheap, since USBFuzzer is running as software on the host. It allowed it to be portable, as an emulated USB device would look the same and just plug in like a regular USB device, and didn't require heavy knowledge of the USB standard. So USBFuzz works by attaching the emulated device to the virtual machine and feeding in inputs chosen by the fuzzer. Since the fuzzer is trying to find bugs in the kernel, how is it possible to monitor the execution and check if the kernel ran into an issue? Well, the authors decided to monitor the kernel logs, instead of just trying to monitor the kernel and see if the kernel had exited or if the kernel had done something unexpected. Just read the logs. The logs will tell you, did it succeed, did something weird happen, and then if it kernel crashed or hung up, you'd be able to tell because the kernel wouldn't be doing anything. So USBFuzz reads the logs and connects whatever the log was, whatever the results they found in the log, with the input generated by the fuzzer, so that they could find which inputs caused what bugs. In order to monitor code coverage, the authors need to be able to see how much code has already been covered. Now, the Linux kernel supports static instrumentation with code coverage based on KCOV. However, KCOV by itself only supports a single process without interrupts and without kernel threads. And so, in order to extend this static instrumentation of KCOV, the authors ended up creating an AFL-style edge coverage scheme that allowed the fuzzer to get this code coverage data from the kernel and mutate inputs based off of the code coverage that they found. Now in this image, we can see how USBFuzzer was set up. This image was taken directly from the paper and describes how the fuzzer communicates with the guest, how the fuzzer and everything in the guest system are set up in order so that the fuzzing device can actually provide these randomized inputs. USBFuzzer runs on the host operating system. It mutates the data and then feeds the mutated data into the fuzzing device, which is located in the guest system. It's as if it was just plugged into the guest operating system. Now the target system is running on a virtual machine, that's why it's the guest system. And this operating system is supporting reading from the emulated device and can support the emulated device. And it supports communication between itself and the fuzzer of the communication device. Now that communication device allows the guest system just to share that code coverage back with the fuzzer, to share the logs back with the fuzzer so that the fuzzer can guide its mutations and guide the input generation to get more coverage. The fuzzing device itself is also just the emulated USB that's sitting on the guest operating system. And all it does is it provides data from the fuzzer whenever the target tries to do I/O operations. So if the target tries to read, the fuzzing device just gets the data from the fuzzer and gives it to the guest operating system. Now you may be wondering, how does the USBFuzzer actually get the kernel logs? Because it's located outside the guest operating system. Operating systems don't typically, feed the logs into the communication device, and the communication device itself isn't grabbing the logs. What happens is that there's a user mode agent, and this is just a user space program running inside the guest operating system, and it's just monitoring the execution. It's checking for the log files, checking to see what's going on, and then it just shares those log files back with the fuzzer. To check the bug finding ability of USBFuzz, they ran it on about 9 versions of the Linux kernel, the specific versions of which you can read on the paper, but they were the latest versions at the time that they evaluated the paper. They fuzzed each version for about 4 weeks with about 4 instances each for roughly 2.8 million executions. In total, USBFuzz found 47 unique bugs in the kernels, with memory bugs being among those that were found. These memory bugs could lead to some crashing, could lead to code execution by the attacker, or could lead to data leakage where the attacker can get sensitive information. Other bugs that were found were simply warnings of some potentially dangerous statements that would lead to an unexpected kernel state, but that would have to be evaluated just to find out whether it is or is not serious. Now I'm sure you're wondering what exactly the bugs are in the Linux kernels and if you could take advantage of those bugs. The table on the slide shows some of the bugs that have already been fixed in the Linux kernel, and there's more bugs that you can take a look at in the paper itself. USBFuzz was compared with SysCaller to evaluate its performance when compared with another USB fuzzer. SysCaller, overall, had more code coverage than USBFuzz. The authors attributed this to syscaller of having had more manual analysis of the Linux kernel, and that because of this manual analysis, a lot more messages adhered to the USB standard. You can actually see this in syscaller's code coverage for device drivers. It was noted that syscaller had a lot of test cases that were fine-tuned for specific drivers. However, for the host, USBFuzz did outperform syscaller. You can see that in the image there where it says host, and you can see that USBFuzz has much higher than the syscaller. And this was because syscaller used a USB gadget, and USBFuzz actually emulated the USB device. Overall, the authors noted that syscaller found bugs where the inputs meet the USB standard and that meets input checking. However, for USBFuzz, the USBFuzz was able to find bugs where the input was malformed and didn't perfectly adhere to the USB standard. USBFuzz was able to find more bugs when the input was malformed and didn't strictly adhere to the USB standard, and this was because the USBFuzz, as the authors say, followed an out-of-the-box approach. The authors suggested that the two fuzzers complement each other and find different types of bugs because of their different methods. Now, what determines how long a test of a USB driver takes? I'll give you a couple of seconds to think about that. Okay, time's up. So you might say, well, it's the input, of course, but I want you to be a bit more specific. So, what really determines how long a test takes is whether the input passes the first sanity checks, which is what the authors noted. They found that when the input fails because of the first sanity checks, then, well, the test ends very quickly because it fails the sanity checks. But if it passes, the time needed to test depends entirely on the driver. And so, of course, more complicated paths, more complex paths end up taking a lot more time to run through. Between both syscaller and USBFuzz, syscaller had about 0.1 to 2.5 executions per second, with USBFuzz doing a very similar 0.1 to 2.6 executions per second. The low executions per second, the authors noted, can be attributed to pretty much how long tests can take on USB drivers compared to just regular programs. Just guess how long the authors found that it took for a physical machine, not an emulated machine, not a virtual machine, just an actual physical machine, to fully recognize a USB device. If you said less than 3 seconds, you're wrong. If you said 4 seconds or over 4 seconds, that's absolutely correct. They said they found it took about over 4 seconds just for a physical machine to completely recognize a USB device. So what would be some good operating systems to test for USB bugs? You probably started off with whatever operating system you're running on right now. Maybe Windows, maybe Mac, maybe you're on Linux. Now, the authors ended up testing multiple operating systems with USBFuzz to ensure that it's portable and works across multiple operating systems. So in addition to the Linux kernel testing that they did, they also tested on FreeBSD, Mac OS, and Windows, but both Windows 8 and Windows 11. And they also tested a USB webcam driver, just to specifically find any bugs in the driver itself. For FreeBSD, Mac OS, and Windows, the operating systems, they couldn't exactly use the same methods that they were doing before, because there is a lack of support infrastructure. There's no coverage information that they can get from these operating systems, so they can't really guide their mutations with that. And so what they did instead was they took the inputs from the Linux kernel where they could get guidance, code coverage, and they could get the guidance for their fuzzer, and they used these inputs for the operating systems. They also found that the fuzzer couldn't find bugs that caused memory corruption because, once again, there was no support infrastructure there. They could only find bugs that caused exceptions and that caused messages to be logged into the logs. And so the authors were able to find 3 bugs on Mac OS, 4 on Windows, and 1 in FreeBSD. And if you want the specifics of what exactly these bugs were, I recommend that you read the paper, because they are all listed out in the paper, what the bugs do, each operating system. The authors also tested a webcam driver as well. They used USBFuzz to emulate a specific device and a specific device configuration of an existing device. This let them test that specific device driver on the operating system, where they found the webcam that they were emulating, that specific webcam they were using, had a bug in the driver of the Linux kernel that caused an infinite loop and eventually caused the system to run out of memory. Now, continue on with the flexibility of USBFuzz. They found that it was very extensible and that they could extend it to any interface supported by QEMU, QEMU. And anything that QEMU is capable of supporting, USBFuzz can support with very few changes. They noted that there's only 3 things that you would need to do. 1, you would just need to implement a device for the interface and adapt the I/O operations to forward data generated by the fuzzer onto the operating system. You would also just need to adapt the fuzzer to attach the new device to the virtual machine. And finally, just let the user agent in the virtual machine detect whatever changes that were made from the new device in the logs, because if you test an SD card, that log file might be a bit different from a USB log file. And so to prove that it was flexible and that you could extend USBFuzz to other interfaces, they extended it to SD cards. The extension from USBs to SD cards only required about 1,030 lines of code to be changed, with the majority of the code, 1,000 lines, pretty much just being implementing the SD card itself. However, after fuzzing the SD card drivers for about 72 hours, they didn't really find any new bugs because of how simple the SD card interface is. Now, I'll give you a few seconds to think about maybe why is the SD card interface just so simple? Why couldn't they find any bugs in it? They found a bunch in USB drivers, so what was different about the SD cards? So the authors noted that the SD card interface was just simple because there were a very limited number of drivers for SD cards in the first place, but that the SD cards just had fixed commands and fixed length, so they were very simple. Overall, USBFuzz accomplished exactly what it set out to do. It was portable because it could be used with a lot of different operating systems. It was cheap because it was just software that you just had to add on, maybe make a few modifications. And it was effective, having found a couple of different bugs. And those bugs that they found, you can find on their paper along with one of the case studies of one of the bugs that they found. So thank you for watching this presentation. I hope you enjoyed it, and have a great day.